Hello, welcome back to the Aspen channel. For those who haven't subscribed yet, please click the button subscribe so that you can subscribe to the channel and click the bell icon so you will never miss any update from this channel. Now, as promised in the last video, that we will be simulating refrigeration cycle in this upcoming video. So here we will be doing the refrigeration cycle. First we read the statement and then we will start the refrigeration cycle simulation based on the statement. In a typical refrigeration system, the refrigerant starts at room temperature and ambient pressure, 25 degrees centigrade, 1 bar, and a flow rate which we are assuming here is 100 kgmole per hour. It is compressed, which increases the refrigerant's temperature and pressure, so it is a superheated vapor. In our case, we are taking it to 5 bar. The refrigerant is cooled by air with a fan so that it is close to room temperature. At this point, its pressure remains high and the refrigerant has been condensed to a liquid. Means the first it is compressed and then it is cooled down. Means we will first use compressor and then we will be using a cooler. Then the refrigerant is expanded through an expansion valve. Its pressure decreases abruptly, causing flash evaporation, which reduces the refrigerant's temperature significantly. So, compressor, cooler, and then valve. And the very cold refrigerant can then cool a fluid passed across a heat exchanger, air in an air conditioner. And then finally we are having heater. And then the loop will close as we have closed the loop similarly in our steam engine. Of course, for an AC air conditioner to work, the air which is used to cool down the superheated refrigerant must be air outside of the room. The air that is cooled by the cooled refrigerant is the air inside the room. That is very clear that how air is cooled down in an air conditioner is due to the refrigerant that is working in the air conditioning system, and the air is cooled down in the heater across a heat exchanger. Currently we will be using here a heater in our simulation, but when we will be learning heat exchanger in our upcoming videos, then we will again simulate this with using heat exchanger in our system. So we are clear that we will be using four equipments today: compressor, cooler, valve, and heater. For this system, we will be using propane as a refrigerant. Select propane and then select Peng-Robinson because it's a hydrocarbon system. We have already been adding component and fluid packages, so I have just skipped this method and I am moving to the simulation. For those who haven't watched previous videos, please watch these. Now I can't find my simulation model plate, so it's no need to worry. Simple go to view and click on model plate. It will appear. So our first task is to simulate a compressor. Click on compressor, place it over here. Click on material stream, place it over here. Open the compressor to check how many material streams you need. You need two material streams and one energy stream. So I will be using both connection methods today so that who uh, find difficulty in the second method can use the first method as well. This is stream number 2, material stream, and this is the energy stream. Click on compressor K100, label it as compressor. Inlet 1, outlet 2, that is Q100. Add values in the parameter worksheet. I will simply say it as refrigerant in. I'm using my nomenclature, you can use your own nomenclature. What are the given conditions? In a typical refrigeration system, the refrigerant starts at room temperature and ambient pressure 25 degrees centigrade and 1 bar with a flow rate of 100 kgmole per hour. 25 degrees centigrade, 1 bar and 100 kgmole per hour. And then in composition, go here, put the value of 1 which is a mole composition. It is compressed, which increases the refrigerant's temperature and pressure So it is a superheated vapor, and given condition is 5 bar. As you know, that degree of freedom for compressor is 1, means we have to enter just one value which is given to us as outlet pressure, which is 5 bar. So you see, it's converged, and vapor value is 1. When vapor value is 1, it means it's in vapor state, and if it's 0, then it means it is in liquid state. Remember this point because we will be using this point in cooler. I can say it C ref out, compressed refrigerant outlet. Next one is the cooler. Coming back to this, the refrigerant is cooled by air with a fan so that it is close to room temperature. At this point, its pressure remains high. There is no significant pressure drop. Very minor pressure drop can occur, which we are taking as 0.1 bar, and the refrigerant has been condensed to liquid. If you remember in our previous videos, and I will remind you in this as well, for cooler we required two parameters. Its degree of freedom is 2, but we have been given just pressure over here. So what to do in this situation? Reread this line. And the refrigerant has been condensed to a liquid. It means it's in liquid state. So no need to worry. Just click E100, compressed refrigerant out. Name it as, this is another way of doing the connection. Cooled refrigerant out. You can say it as Q101. In last simulation we used different nomenclature, so there is no need to worry about that. Given value is 4.9 bar. No temperature value is given. It means you are left with this value, which is the vapor, and you have been given the condition that it has been condensed to a liquid state. So I have earlier told you in this video few moments ago that for if it's 1 it's in vapor state, if it's 0 it's in liquid state. So simply enter 0 over here and you can see you have got the answer. So again you have entered two parameters, vapor and pressure over here. Okay, that's very simple. Then what is going next? Then the refrigerant is expanded through an expansion valve. Its pressure decreases abruptly, causing flash evaporation, which reduces the refrigerant's temperature significantly. And given parameter is 1.5 bar. Remember, degree of freedom for for valve is 1, and you will learn these once you go through the exercises. The outlet of cooler is inlet of valve. Cooled refrigerant out, heat refrigerant out. Very simple, and you have to enter the pressure over here 1.5 bar, and flashing has occurred, which is depicted by this vapor value that it's not now 0, it's multi-phase, two-phase mixture. I will just modify its name and modify its name to valve because we have to use the proper nomenclature. And the last thing, the very cold refrigerant, as you can see it's in negative state, negative value of temperature, means very cold, can then cool a fluid passed across a heat exchanger, means it will be heated up to the same temperature as that of inlet. Let me show you. Heater, valve refrigerant out, refrigerant in, Q102, and you can see it's converged and the whole simulation scheme is converged over here. Heater, it means that it has been heated from minus 32.84 to 25 degrees centigrade and the loop is closed. This refrigerant from the heater will again be compressed, will again be cooled down, again flashing occur over here, and again be heated. And when it's heated, it means the other stream will be cooled down. That will be the air which is passing through this heat exchanger, which will be cooled down, and then you can feel the cold air in your office or in your room, etc. Okay, so that's how you can simulate a refrigeration cycle. Let me repeat it, that first you compress the refrigerant, which is at inlet, whose inlet conditions are ambient conditions, compressed it to a higher pressure, then it's cooled down where it is condensed to a liquid state, and you have mentioned it over here that you were not given the temperature value but you were given the condition of the refrigerant which was in liquid state. So vapor value is 0, means it's in liquid state. Then throttling expansion occurred through a valve, which you seen that sudden change in pressure and then heating, and then this loop is closed. So that's the today's simulation scheme. One thing which we will more learn today, that this scheme is not looking great. So how to make it look much better here? You can simply go down to flow sheet modify, and coming here, automatically position all operations. So just click it over here. Are you sure you want to reposition all the objects in the flowsheet? Click here and you can see it's much better now. You can just drag it down over here and you see it's looking much better. So please do watch the video, like the video, subscribe the channel, click the bell icon, and please do share comments and your feedback for the improvement. In the next video, we will be generating steam tables in Aspen HYSYS. Thank you so much. Stay tuned.